Maybe we can start. Yeah, let's start. Okay, so hi everyone. So today we have the pleasure of having Athira Menon, who is going to give the seminar. Sergio, I think you will introduce her, but just before this, two things to everyone so that the streaming goes well. Please mute yourself and also remove the camera so that there's no problem with the streaming. And to the students, I already sent a private message that send me a message if you are attending the talk, and I will put you on the list. So Sergio, you can introduce the speaker. Thanks.
Okay, thank you, Arita. So it's my pleasure to introduce today Athira Menon. She is a visiting scientist in the University of Amsterdam, at this moment working at a distance. No, you're there in India. So thank you very much for joining today, despite it's a bit late. She did her PhD in Monash University in Australia in 2018. But before that, she had the opportunity to travel a lot, as I've seen in her CV, making the master and bachelor in the University of Victoria in Canada, University of Canterbury in New Zealand, and also in Mumbai. And before summarizing a bit her interest, specific interest, I would like to say that beyond her very interesting papers on stellar astrophysics, she was also award-winning in science communication, a science communication speaker in a global contest, and she was also invited as a speaker in TEDx. So I encourage you to go to YouTube and look for her name and see the talk he gave, because it's very, very nice and very interesting. So during her young career, she has been mainly interested in understanding the lives of massive stars, especially in the study of binary systems, and from an observation, from an evolutionary point of view. And to this aim, she not only developed a specific model of individual binary systems, but also he did models for synthetic stellar population, no? And in both cases, with the final objective of linking the outcome of this computation with specific observation. So she was also has been recently part of the ERC funded project Beam Cosmos, being led by Selma de Mink in Amsterdam, and I'm sure she's going to deliver a very, very interesting and nice talk. So go ahead whenever you want.
Thank you, Sergio, for that great introduction. It's my pleasure and a privilege for me to give this talk all the way from Mumbai, which is my home, during these tough times, and still have interesting and productive scientific discussions with the larger community. So thank you again for the chance. And let me start right away by sharing my screen. Okay. There we are. So most of my work in stellar astrophysics has had to do with some form of stellar mergers, and that continues to be the case. Today, I'm going to speak about what I did at Amsterdam for my postdoc. And this is a glimpse into one of the longest, possibly the longest cosmic union which we can witness in our lifetimes. And these are of contact binaries, particularly of massive contact binaries that are existing in the Magellanic Clouds. What you see right there in the image is an artistic rendition of one such hot, massive contact binary. Together, the two stars are 60 solar masses in total. And as you can see, they're exchanging a great cosmic kiss. Probably has been going on for a few million years right now. That is VFTS 352 in the Large Magellanic Cloud. So let me start. Before I begin, I welcome questions along the way, so please feel free to interrupt and to ask anything you like. Okay, so it's almost axiomatic today to say that massive stars don't really like to live alone. They have companions, sometimes more than one of them, to which they're gravitationally bound. And there's a nice animation there about a couple of stars going around a common center of mass. These are binary star systems, and they are characterized by three main aspects: their orbital period, the total mass of the system, and the mass ratio, which is the ratio typically of the less massive star over the more massive one. And you have a figure there which shows you the distribution of O-type massive stars. So these are the really massive ones, over 15 solar masses at least. The binaries in a sample of galactic young clusters collected by Uksana sometime in 2012. This result was published, and it was a big result because it actually confirmed what we knew over surveys done in the past, that at least 70% of the massive stars in the galaxies, the more massive the star is, the likelier it will have a companion, but 70% of them do have companions and they live in binaries. And of course, Sergio himself is leading the IACOB survey, and he knows all about this. This was a groundbreaking result in itself. In the Large Magellanic Cloud, there was another survey, the VLT Flames Tarantula survey, which also collected possibly the most homogeneous sample of massive stars. And there they found that the fraction was around 50% of massive stars living in binaries. So binaries and massive stars are very important for us to consider. Their contributions have to still be quantified and characterized to a stellar population. And this is still work in progress in stellar astrophysics. Now, what you will observe in this diagram already is that you'll notice that the clumping, the number of stars, the number of binaries, they're favored closer to the lower orbital periods, which means close binaries form much more favorably than wider binaries. So if binaries form this close, they will interact, right? And in a binary system, the way stars interact is by transferring mass from one star to the other. In that sample, the one that I showed you earlier, about 30% was inferred to be effectively single, which means these stars are not interacting currently, and they may not interact in the future. They will evolve as solo stars on their own way. But the rest 70% of those O-star binaries will end up interacting in some way or the other. Of that, at least 25% are expected to merge. Stellar mergers are a very young topic in astrophysics, mainly because it's so complicated. Many uncertainties hanging around there. But it is an important thing to consider because when stars merge, they can masquerade as single stars in a stellar population. And that can really change how we look at stars themselves. Was it born single, or did it merge to become a single star, right? And there are many peculiarities among stars that can be attributed to stellar mergers from our preliminary models. So what I'm having here is the previous pie chart, but also just something very basic. I'm sure all of you know it. It's called a concept of the Roche lobe. Binary stars are typically classified into three types depending upon the possibility of a mass transfer and that nature of the mass transfer itself. So what determines whether a star will transfer mass to its companion is whether it will overflow what is called a Roche lobe, which is an equipotential surface drawn around a star, exceeding which the star cannot retain its material. It will let go of that material. It can be expelled outside of the binary system, or it can be accreted by its companion. So if a star underfills its Roche lobe, both stars in this case, it would be a detached binary, and that's the first panel. A semi-detached binary if the amount of mass is only going from the more massive star, or the star that's puffed up, and it's giving away mass to its companion. These are called semi-detached binaries. And the star of today's talk, of course, is the contact binary in which both stars overflow their Roche lobes simultaneously, and mass can be transferred from one star to the other, depending on certain conditions. Now, there is a strong link between contact binaries and mergers, and I'll tell you a little bit more as we go along, but this is why we need to understand contact binaries well. They are a key important thing to understand in order to understand how stellar mergers themselves work. So let me go ahead and talk a little bit about the kind of stellar mergers possible. And that would depend on when the stars end up merging? What is the morphology of the stars themselves when they end up merging? Are the stars on the main sequence when the merger happens? Then this is a case A merger. And this can lead to many interesting outcomes. You could have a rejuvenated, rapidly rotating main sequence star, or even magnetic stars. That's one thing that could happen from a case A merger. A case B and case C mergers happen when you have a main sequence star merging with a puffed up giant. Either it's on the Hertzsprung gap before core helium burning is completed, or post core helium burning. And this leads to a plethora of interesting objects coming out of the merged star, something I personally worked on, and today as well, I will welcome questions on it. My PhD thesis was on the progenitor of supernova 1987A, which is most likely to have come from a merger of a main sequence star and a post-helium core burning giant. Light curves, the location of its progenitor, where was it in the HR diagram, etc. All of these conditions could only be met if we considered a merger model. So generally, mergers are very important to study. So if you have a close main sequence binary with an orbital period of a few days, it's likely to interact when both stars are on the main sequence. And here is a video done by ESO and NASA to show you what that VFTS 352 star looks like. This is the hottest contact binary we know amongst massive stars. And this is an inevitable phase of evolution when you have binaries that are bound so close that they orbit each other every few days. So what happens next, right? Okay, so a system enters contact. What would be the future evolution of the system? There are two possible ways it can go. One is it can go through a common envelope episode. Now, of course, this is a little bit tricky. The surface is common even in a contact binary, but a common envelope episode is a bit different, and I'll get to that in a little bit after this slide. Once the stars enter a common envelope episode, the outcome that's going to come out of it would be a stellar merger. That is, the stars will merge as stars and form a new star, and that could end up becoming something very peculiar, different from a regular main sequence star. On the other hand, it is possible that the two stars actually don't ever interact again through after the contact phase. It is possible that a certain strange evolutionary channel called the chemically homogeneous evolution kicks in, which detaches the two stars because they become compact. And then the stars evolve like single stars. Maybe eventually they could collapse to black holes. And the black holes could then end up merging. And this is often considered as one of the main channels of evolution to have produced black hole mergers, which LIGO has detected over the last few years. So this is one of the main reasons why contact binary evolution is very interesting to study. So again, this must be stuff you already know, but again, it's good to set the scene very clearly. What you see here is a nice Blender animation of what a common envelope episode looks like. You have a star that's already puffed up, and it literally envelopes or engulfs the secondary star, the main sequence in this case. And the main sequence star spirals in because of friction towards the core of this puffed up star and is shredded apart by its gravity, and eventually everything mixes up together to form one big star. It ejects some of its mass, and then it ends up becoming a star in thermal equilibrium, and eventually that itself will either explode or collapse directly into a black hole. And this is the channel through which, in fact, 87A's progenitor is considered to have gone through. So that is a common envelope episode. Here is the chemically homogeneous evolution channel, not so common channel of evolution. On the top, you see, in fact, what happens during a regular main sequence evolution of a star. You have a star. It has just begun its life on the main sequence, so it's starting off as a hydrogen-rich blob of gas. And then as it burns through, it starts forming a core and an envelope structure, right? The core is burning hydrogen to helium, and you have the envelope that's rich in hydrogen. Now, this star on the top again will continue to expand as it moves along the main sequence. And if it has a companion, it could overflow its Roche lobe, and the rest of the story continues. But at the bottom, you have a different story. Now imagine the star started off again on the main sequence, just beginning its burning of hydrogen to helium. But this time the star is rapidly rotating, a good fraction of its critical velocity. What happens in this case is that the star cannot retain its core envelope structure. Why? When the star is rotating fast, there are these rotational induced instabilities which cause mixing in the star. So what happens is helium, which is burning in the center, is taken to the surface, and this is so efficient, what you eventually get is just the core of the star, which becomes blue and compact. There is no envelope, it does not puff up, and at the end, you have a star which is just a helium star. And this is precisely why we can get detached binaries coming out of the contact phase. Let me show you how that happens next. Yes, before that, of course, another important thing to know about how to identify these homogeneously evolving stars. If you have an HR diagram, here you will see there are two tracks. There's the normal evolution, which is a regular main sequence star evolving to the right. It gets cooler with time. And to the left, the star actually gets hotter and hotter because it's becoming more helium-rich and more compact, and it evolves towards the left. Here, this is for a single star of 40 solar masses in a very metal-poor environment. Let us see what happens in a binary. So in a binary, the situation requires some mechanism to get stars to rotate rapidly. What if the stars are not born with very high velocities? How do you get them to rotate rapidly? Then in this case, you start out with two stars on the 0H main sequence, very close to each other, orbital period of a few days, depending on the mass, etc. And then what happens is that the stars will enter contact, right? Because both stars will puff up and overflow their Roche lobe simultaneously. And in this situation, when the stars enter contact, tidal forces kick in. What tides tend to do is to synchronize the rotation velocities of the two components with the orbital period of the system. So there is a possibility in this case that the two stars can spin up so rapidly that they become homogeneously evolved, right? So in this case, the two stars will end up evolving homogeneously. They will detach, shrink, and then go forward as solo stars until finally they make black hole binaries, which could merge again in the Hubble lifetime and give you nice gravitational wave chirps. So contact binaries are therefore interesting in this regard as well. But there are certain conditions under which this homogeneous evolution can occur. You need rapid rotation, of course, but you also need a really low metallicity environment. Why is that? Because with high metallicities, you have more powerful stellar winds, which can take away not only the mass of the star, but also the angular momentum of the star, and therefore from the system. This would actually end up slowing down the rotational velocity of the star, and so it's not quite possible for them to have simply a core. The gradient of the composition could be continued to be maintained. So you need a very metal poor environment, rapid rotation, and more massive stars typically can sustain homogeneous evolution as well through rapid rotation. Here is a set of tracks on the right for different orbital periods. This model is of a 50 and 25 solar mass star. For the small Magellanic Cloud, which is about 1/5 of solar metallicity. And you can see that with smaller initial orbital periods, you have homogeneous evolution on the left, and on the right, the stars veer towards a redward evolution because that's just normal main sequence evolution. Okay. So contact binary phase, the first takeaways are this is an inevitable phase of evolution in close massive binaries that are born with orbital periods of a few days. And they're very important because they will help us constrain what fraction of these binaries will end up merging as stars, as against which ones can actually make it all the way through to become progenitors of gravitational waves. They are also great because, as I said, it is a long cosmic union. You can see this happening over millions of years. We are witnessing something over the nuclear time scale, of course, which is a large fraction of the main sequence lifetime of the system. And it's great because we can actually test our current stellar models, the physics of them, against something as extreme, I would say, as this configuration. So we can test the efficiency of rotation mixing, is the possibilities of homogeneous evolution. What would be the effects if mass is expelled from the system? How would that change the dynamics of the binary, and of course the impact of tides as well? Um, Previously, this phase in massive stars actually has been just glossed over and not particularly focused on. There has been no study so far that tried to compare what our models can reproduce when they look at the properties, the stellar parameters of these contact binaries. So this is the first work that I'm going to present, which actually attempts to do this. Now, I'm not an observer, but it is important for theorists to know how things are done. This over here is how contact binaries are found. This is typical for all eclipsing binaries, actually. You need two things. You need to know the light curve variation, the light curve cycle of the binary system. And in this case, it's a beautiful sinusoidal curve with almost a fixed amplitude because the stars are so close and they share a common surface. And the minima happens when one of them comes in front of the other only, but otherwise it's a nice continuous wave, sinusoidal wave there. And of course the radial velocity curve as well. And these can tell us all the details, the parameters of the system can be derived. What I have here is in fact for VFTS 352, as I mentioned, both the stars together add up to 60 solar masses, but also it's interesting that both stars have nearly equal masses as well. Not sure if they were born like this or did they actually achieve that through contact? Well, we'll find out in the rest of the talk. Okay, so I have accumulated here all the massive contact binaries we know. On the left for the Magellanic Clouds and on the right for the Milky Way. So you will notice that the Magellanic Cloud contact binaries are all located near the 0H Mink sequence. And for the Milky Way as well, that's the case for the majority. But a few are actually further out. They have seem to have attained contact a little bit later in their lives. These are the oddballs in this population, and maybe we can together in the talk try to figure out why or how these may have formed. Otherwise, these contact binaries are found very close to the 0H main sequence, where they began their main sequence lifetime. Now we get into actually how we model these binaries. And this is my work, and it's on arXiv. They are almost close to publish this work in MNRAS. So the model grids that I did were for the large and small Magellanic Clouds. I will admit the motivation initially for that was to see what conditions are required for homogeneous evolution, whether we can get gravitational wave progenitors in our neighboring galaxies. I can tell you already that answer is no. But this is the reason why we chose to only model these two populations. So the range of initial parameters are listed on the left. You have the initial mass ratio that we explore is from 0.6 to 1. And the total mass of the systems are from 20 to 80 solar masses. Again, the combined masses of each binary. The initial period is from 0.6 to 2 days. I'll tell you why this range is chosen. And the metallicity corresponds to what the large and small Magellanic Clouds have, about half and 1/5 of solar. The code I used to compute my models is that of MESA, and it does have a prescription for the treatment of the contact phase. I do not have a slide on that in this talk right now, but it is there in the reserve set, and maybe if you're interested, I can tell you how this phase is implemented. But briefly, the way it goes is that this is a complex 3D scenario, right? And we work with 1D codes because we don't have fast-lit computers to do things in 3D, at least for now. So in 1D, what we do is we consider the rate of overflow, the expansion of each star separately, and then decide how the mass has to be transferred from one star to the other to maintain a certain relationship according to a fit function that has been calculated separately. So this is how we go about evolving the star in contact. And we can talk about this later. But this prescription has been implemented by Pablo Marchante in MESA from his thesis work. And another assumption we also make for the first set of model grids that we have here is that the transfer of mass is conservative, which means that when mass is transferred from one star to the other, it goes entirely to the star. We don't assume anything leaves the system. Of course, there is mass loss through stellar winds that happens, but mass transfer through the binary interaction itself is conservative. So these are the way that we go about making the models. An important thing to consider while looking at these contact binaries, because they're so close to the zero-age main sequence, is how you initialize the models. Now, there are many ways to do this, but what we decided to do is have sort of a standard calibration so that we can make reliable predictions about how these things evolve. So the way I have decided to do it for this work is I have made sure that each star in the binary is at its lowest radius on the main sequence before it expands and takes off. So the zero-age main sequence, according to my definition, is the minimum radius of the star before it burns hydrogen to helium. And the line that I have drawn there is to show you where the initialization occurs. So we are essentially saying in our models that both stars have achieved minimum radius before taking off and interacting further in their lives. That is a key assumption we make. And another thing we do also is that when the stars overflow the L2 Lagrangian point. So how do we do this? You have the Roche lobe surface. The L2 Lagrangian point is the one on the right of the lower mass star. Now, if material starts leaving that point, we assume that the situation is a bit unstable and there will be a common envelope episode. That means the secondary star will be engulfed in the envelope of the primary, and we assume naturally that the common envelope phase will lead to a stellar merger, like I showed earlier. So then the evolution is terminated as soon as the model overflows the L2 or the outer Lagrangian point. The evolution is also terminated if one of the stars leaves the main sequence. Why? Because they're simply interested in the main sequence binary population, in the synthetic population. That's it. We just want to know about the main sequence lives. So those are the two conditions under which the evolution is terminated. Okay, so let's now look at how exactly the evolution itself occurs. I have broadly categorized the evolution of closed massive binaries in my grid into two types. The first one here is system 1. What you see on the left is the HR diagram. The right are the evolution of the Roche lobe, sorry, the radius of the star over its Roche lobe radius, and at the bottom, the masses of the star. Here we are looking at a system that has begun with an orbital period of 0.8 days, a mass ratio of 0.8, and a total mass of nearly 26 solar masses. So let's begin on the HR diagram. You have, can someone tell me if you can actually see my pointer?
Yes, we can.
Yeah.
Oh, super, great. So it starts here, the evolution, the circles over here. And at some point, it enters into contact at point A. This is roughly within 0.05, 0.1 million years. Once the system enters contact, the system maintains contact until it experiences an L2 overflow. That means this system will end up merging on the main sequence. This is a long nuclear timescale, right? For almost all of its lifetime, this system has attained contact and not broken. And by the end of the evolution, actually not by the end, very soon after it enters contact, you can see that the masses equalize. So throughout this time, it's got an equal mass. Each of the stars have got equal masses. This is reminiscent of the system we just saw earlier, which is VFTS 352. Even though it started off with an unequal mass ratio, the system ends up having equal masses. And this may be how that system, the VFTS 352 system, began and is progressing through its life. So this is one of the channels of evolution that we see. Now, the same system, the only difference is that we have started off with an initial orbital period of 1 day instead of 0.8. Again, now the stars start off, but when they first come into contact, it is not simply, they don't simply maintain contact. There is first a thermal timescale mass transfer, a fast mass transfer. Immediately the masses flip, as you can see in the bottom diagram here. I must explain one more thing. You can see two lines. The dashed line is the secondary star, the less massive star initially, and the solid line is the more massive primary star. So the masses flip after this thermal timescale contact phase, and at the same time, the less massive star now continues to evolve, but it also transfers its mass to the more massive star. So you can see that the secondary star continues to build on its mass, but the less massive star is coming down. And that's only because it exceeds its Roche lobe while the other one doesn't. Thereafter, you have the stars entering contact again, and now it enters contact over a nuclear timescale. And once again, the more massive star decides to transfer mass, and the system achieves a final mass ratio of Q equal to 1 before merging. And that's what you see here in the HR diagram as well. So those are the two types of contact binary evolution. Let us now proceed from here. Just, excuse me for 1 minute, please. Okay, so those are the evolutionary channels for the binary evolution of the contact phase. Let us now look at what happens when you take the bigger picture, right? We are looking at a small subgrid of my models. You can see that this set is for an initial mass ratio of 0.95, right? So very close to 1, but not quite. On the y-axis, you have the orbital period that the system starts with. On the x-axis, the total mass of the system. The colors in the background, the various pink shadings, are the contact durations. And you can see that they actually range from 0 all the way until 11. So the longest living contact binary in my grid here has around 10.5 million years or so. That's how long those systems stay in contact. And they are, of course, for the lowest mass binaries around about here, 20, 22 solar masses in total. Like I said, the pink shading represents the contact duration. Then you have other colors. Hatchings show you systems that evolve as system 1, which means these guys will end up having or achieving equal masses during the contact duration itself. And the rest is system 2, which don't have any shadings. Some systems come in contact and merge right away. Those are the initial L2 overflow systems over here. And the ones with the stars are those that actually make it past the main sequence without merging. At least one of the stars gets out of the main sequence. The system avoids a merger as a main sequence binary. So this is what happens for this configuration when you start with an initial mass ratio of 0.95. On the other hand, if you look at, say, the more extreme mass ratio of my grid, which is 0.6, you can see that fewer binaries achieve equal masses during the contact phase. You can see where the lines are. What happens in this case is that most of the systems enter a thermal timescale contact and end up detaching after that, you can see more of the systems actually survive the main sequence evolution. And what this leads us to understand is if you find closed binaries with a short orbital period, right, it is likely that they must have begun with unequal masses over here, more extreme unequal masses. But nuclear timescale contact, whenever this is achieved, it's very likely that these stars will end up having a mass ratio of unity before merging. So that is the first takeaway message. Contact binaries evolve towards mass ratio of 1. When systems evolve like that of system 1, the system enters contact and will remain so without breaking contact until finally a merger occurs. In system 2, you can have not necessarily a mass ratio of unity from the contact binary. You can have a varying range depending on when the system merges, but even these are likely to merge on the main sequence. Very few binaries actually can leave the main sequence without merging. Once contact is established, they will end up merging. This is very likely. But those that do have an orbital period initially of at least 1.5 days, not less than that. Those are systems that end up merging. Another important thing that is not mentioned here yet is that I did mention the grids were done for the large and small Magellanic Clouds. The results that I have shown you here are somewhat similar for both. I have shown you so far the large Magellanic Cloud results, but for the small one as well, the results are somewhat similar in case of the contact duration and the manner in which the systems evolve. Okay. So now I did promise you we have done a study that compares with what we observe. And for that, we need to build synthetic populations out of the model grid. In order to do that, I've taken the around 2,800 models that I made for each galaxy. And then using certain power laws, which are, again, quite textbook stuff, these are initial distributions for the mass ratio, and the period, making certain assumptions like we assume that the mass follows the initial mass function is that of the salpeter one, which is the most common one we use, and that we assume also that the mass ratio and period distribution are flat as well, flat in log period in this case, and also in the mass ratio. Using these, we go ahead and build synthetic populations and then compare with the distribution we observe in reality. So what we are doing in this first, again, this is a first study. So what we're doing here is we start off by looking at the period and the mass ratio distribution of O-type contact binaries. Okay, so in the plot you see here, it's a bit busy, so please bear with me. In the background, there are two histograms in blue. One has an empty shading, so it's the one with the solid line. That represents the SMC's histogram. And the one in the lighter blue is of the LMC. This restates the point I made earlier that the distributions are nearly the same between the large and small Magellanic Clouds for the period. And also overplotted are the range in the surveys that have accumulated data for massive contact binaries. You can see what range that is. The lower ones, BFTS, the macro sample, and the oval sample are all for the large Magellanic Clouds. One must, of course, remember there are observational biases in place for all of these results. And we'll get to that in a little bit. But you can see the range in period that is available from the surveys themselves. And on top, in gray, is the range in period of contact binaries for the Milky Way. And that's actually going out of the scale of my plot here. It goes all the way up to 6.6 days. So it's in itself a great trend to see. In the large Magellanic Cloud, which is half of solar metallicity, the largest period we know is roughly 2 days for a contact binary, and that one goes all the way up to 6.6 days in the galaxy. So now when we actually do a 2D distribution, in the left here, I've got my 2D histogram plot for the contact period against the total mass while the system is in contact. Few things here that we can intuitively understand is that the clumping, and of course the background colors, I should explain this as well. The darker the color is, the bluer the color is, the more likely that combination of P contact and M contact is possible, right? And that's how the histogram in itself works. So the clumping occurs all in the left corner of the 2D histogram. You can see that for one thing, the plot here is weighted not only by the initial distribution, but also the duration of contact of the system. So lower mass systems obviously end up living longer. Therefore, most of these systems are all clumped in that corner there. So immediately from our plot, one thing we can ascertain is that the trend we see, the trend that we can reproduce with our models is for systems which have a total mass less than 40 solar masses and periods that are less than 2 days or so presently. And there are a bunch of things we can't explain on the right side of that. Let us come to that in a little bit. So here I have the HR diagram from before, and again, in all the systems on the right as well. The observed systems are the circles. The Milky Way systems are the ones in gray. And these are the more problematic ones, I would say, which really stick out, which we cannot reproduce. Glaringly out of place are the ones with very high orbital periods. All of those are marked in the top quadrant. And in fact, what matches here is that these are the ones that are much further evolved along the main sequence. These are not along the zero-age main sequence at all. So something strange did happen during the revolution and cannot be explained as straightforwardly as possibly the others. So we can keep these out of our discussion for just a moment, and we have an idea about how to tackle these, but in a bit. Okay, so the plot here, the 2D distribution here, is of P contact against Q contact. Q contact is, of course, the mass ratio during contact. And as one might expect, overwhelmingly, the distribution favors Q equal to 1, between 0.9 and 1. Most of our predicted distribution says that most contact binaries should have a mass ratio between 0.9 and 1. And not only do they start with nearly equal masses, even the ones that have unequal masses tend to evolve towards Q equal to 1, because they are the ones that actually even end up living longer. But you see a general trend here between P and Q. As Q becomes smaller, as Q becomes smaller, the contact period seems to be rising. And that's what we get as a curve in our distribution. But they again do not quite explain all of the sample set. You have really massive stars in the LMC as well, which cannot be reproduced here. So let's see what we can do with that. One of the main things, as I mentioned earlier as well, is to understand how observational biases work, right? In the case of the Tarantula survey, the biases were that we are considering stars brighter than a certain magnitude and assume those are the massive stars. I believe that magnitude cut is around corresponding to about 15 solar masses or so, but our lowest mass binaries go down to 10 solar masses. So what do we do here is we, on the left, have the normal distribution, and on the right, we have
I think we lost the speaker. Can you hear me?
Yeah.
Oh, okay. I thought I also got I guess this can happen with the internet connection. Let's see if she connects back.
Hello?
Hi. Yes.
Sorry, the internet dropped again, so apologies for that.
No worries. No worries.
Okay.
Yeah.
I'll just
Go ahead.
continue from where I got cut off.
Maybe if
Can
you
I
prefer.
share the screen?
Oh, sorry. I need to put you. Okay, you should be able to do it. And if you prefer to remove your video, I mean, depending on how you can also do this for the streaming. You're muted.
That's okay. Yeah.
Okay, just as you feel. Oops. No, so you're muted. That's normal. Okay.
Okay, right. Sorry about the interruption. But okay, so we were talking about how to make the distributions try to fit better. The way to do that, one of the things we could try to do is to see how the total mass cut would work. I was talking about how in VFTS, the magnitude limit placed corresponds to a star which has at least 15 solar masses. So if we assume that the total mass of of VFTS sample, the minimum total mass is about 30 solar masses, then we get a different distribution, which kind of agrees a bit more with what we actually see in reality, and that is the one on the right. Now, there is the possibility that the true nature of contact itself is not quite real, in the sense that both stars may not be actually overflowing their Roche lobes 100%. In some cases, there are uncertainties which lead us to think that only over 90% of the Roche lobe is overflowing, and yet the stars are called contact systems, right? So, what would happen if we consider near contact systems in the population, which means stars which are overflowing over 90% of their Roche lobe volumes? So again, the same diagrams are shown here, but now for this filter for including the near contact binary. So you have on the left P contact against the total mass, and on the right, in the x-axis, Q contact as well. Now, while of course we won't really expect a difference in the left 2D distribution, because that depends on the lifetime of the stars, and that favors the lower mass binaries in the models. On the right, it little bit looks more promising, I would say, because here we are considering even the semi-detached systems that I showed you earlier. So you can see that the space is filled out a little bit more. You can actually get contact systems with mass ratios going down up to 4.4, which is not possible if you consider only complete contact systems. So this seems to favor the distribution a lot better. So another conclusion we could draw is that the observations are including systems which are in near contact as well. Of course, this still does not explain some of the more massive binaries and the ones with periods greater than 2 days. Let us look at what might be the reason for that. But before that, what are the robust results we can draw from this work? Our work does expect that most contact binaries, the ones we observe, must be having equal masses. That's one. If a system spends nuclear timescale in contact, that must be the case. And that is the case, then also we expect for the observed systems that they must evolve towards a final mass ratio of 1 before merging. And none of the systems in our sample, in our models for the large and small Magellanic clouds actually undergo homogeneous evolution. This does not work for the conditions we have assumed. So with these assumptions, our models don't predict any gravitational wave progenitors with these assumptions. These timescales in contact are unexpectedly large, 10 million years for a system with 20 solar masses in total. It's quite long, yeah? This was not quite known before, how long these contact durations can go on for. And we also can reproduce quite satisfyingly the PQ trend towards the lower mass systems, the ones that are actually close to the zero-age Mink sequence, not so much for the stars that are much further evolved. Metallicity, yes, that's important as well. For the range we've considered between half and one-fifth of solar, it's not making much of a difference to the evolution of these contact binaries or their predicted distributions. Now, I did mention about the Milky Way binaries being a bit off. One of the reasons for that could be one, um, these are high metallicity stars. So one thing that's important is to consider the effect of stellar winds. Um, and that could have big implications for their evolution. And the second thing is the effects of inflation. Envelope inflation is something that we have to really look into. This happens when stars evolve, and when the stars are more massive and with really high metallicities, these stars end up puffing up, having a low density envelope. It is possible that these inflation effects may be the reason why those wide orbital period binaries we saw exist, and they happen much later along. Um, Another thing we have to yet consider is non-conservative evolution. So I did tell you that we assume all the mass that is transferred goes from the donor star to the accretor, nothing leaves the system. But when there is thermal timescale mass transfer, it is likely that some of this mass actually escapes the system. So this could also end up in widening the orbital period. And again, this may be true for the higher metallicity systems. So we cannot really sit here to say that our models are completely representative of the Milky Way population. They're indicative of what should be done in the future about them, what we can expect about them. They need their own set of models and work to be done, which we will do in the future as well. Another thing to consider, of course, is the question of rotational mixing. Very recently, Ben Hastings did publish a work that showed that tidal distortions can cause enhanced rotational mixing in the stars, which means this would impact the abundances and the appearance of the star as well. This is not something we have considered in our work yet, but it is, again, an indication of what we should do in the future. So along with all of this, there is other data available for contact binaries. This here is a set of plots that show you the abundances of carbon, nitrogen, oxygen for one of the stars in the VFTS 352 system. The red region actually shows you where the error bars are for observation, while the single star tracks there, the ones with the black lines, are taken separately. They are from the Brott et al. Tracks. It doesn't matter. What's important here is that this, regardless of what kind of binary model we use or what kind of rotating single star model we use, we cannot really reproduce the abundances. And these are first results, right? These are test models, test results. Something is strange about the abundance trends that we are seeing in VFTS 352. It's not as enhanced as we would expect it to be for a star that's tidally locked. These are fast rotating stars, but the enrichment seems to not be as high as we would like them to be. So this is something puzzling, and this is food for thought. I will end my talk here saying that I hope this first work about massive contact binaries has piqued your interest in these systems, and they're extremely important because they will help us in constraining the progenitors of gravitational waves, which we cannot see yet. They're in the distant universe, by knowing what fraction of closed binaries will merge on the main sequence and not make it all the way. Thank you very much.
Thank you very much, Athira. I'm going to clap for all the people who are attending the talk. That was very interesting. I'm not at all in this field, and there are many interesting things, and I will have some questions. But first, before I ask any questions, let's see if anyone has questions. You can raise your hand or unmute yourself. And I also encourage students to ask questions since I think that would be good. No naive questions are always interesting. So, okay, so I don't see anyone raising hands yet. So I had a few. Oh, Danny, do you have a question?
Yeah, I have a question for Athira related to the point about mass transfer, which is currently assumed to be conservative. Would you expect, if say you relax that constraint, would you expect it to depend on the initial mass ratio?
Oh, that's a good question. I would, in fact, expect that. But before making any further predictions about what might happen, one has to run these models firsthand and check how the efficiency of mass transfer is correlated with the initial mass ratio and what impact that might have. So yes, I do expect there to be some strong relation there.
So in that context, it might be useful to look at, I think some of your contact systems that have been observed in your list have unequal mass ratios, in which case the transfer should be proceeding on thermal timescales. And if it's not conservative, you might look for circumstellar material around those systems.
That's right, yes. That is something to look into. I don't think we have direct evidence from observations yet regarding the presence of these disks. But one, indeed, if there is conservative evolution, it should exist around them. That's right.
Okay, thank you. Nice talk.
Thank you very much.
Okay, thanks. Any other questions? Okay, so I was wondering, so, well, it seems you don't have so many observations, right? I mean, well, I'm used to thousands, hundreds of thousands of stars, so that's, so are there any plans of having more observation? I know you're not in the observation side, but to compare more with your models and have more insights on this.
So I do know that the Leuven team, Michael, in fact, over there, who's a postdoc, who did some work on the abundances of BFT 352. He's looking into finding massive contact binaries in the SMC. So the slide you see here actually just has one massive contact binary in the small Magellanic Cloud, and that's this little guy here. That's it. But that's been done a long time ago, the work for this, and we hopefully will find new results in the coming years.
Okay. So maybe I will ask another question. I was wondering, so some of these, since you're on this plot, some of the outliers, like the ones that are not within your grid, are these mostly the evolved stars? Is that correct, or did I misunderstand?
They're also, so the outliers that are circled here are the more evolved ones along the main ones, but then also the more massive ones as well. So I can show you that in this plot. This entire island over here on the right are after 40 solar masses. They're also not reproduced by our population. One reason for that, as I've mentioned, is the mass cut that we use. Lower mass stars are generally more favored, but also the main reason, in fact, is that inflation effects kick in, which is when stars are more bloated, and this may be something we have to look into in more detail, and that might explain why they have such short orbital periods despite being massive. So we have to see how that works.
Okay. Yeah, I was thinking if some of the evolution, like the more evolved, they had some of the evolutionary effect that maybe we didn't understand model well in our current models.
Yes, and yes, maybe even non-conservative evolution is a possibility for this. We have to again see what happens.
Athira, this is
Yes, Sergio.
Sergio. So could it be that these systems are coming from triple systems in which you have a merger at some point, and then you have a binary that undergoes contact, but in a more evolved phase, or?
Yes, in fact, in the Milky Way systems, a lot of them actually are triples. They have a third component, not the VFDA sample, but the ones over there. Although we're not quite sure what the impact of the triple has, except on circularizing the inner binary and maybe getting them closer. It would be interesting to see what would happen if we put a third star in an orbit around them, and whether we can get this trend to happen.
And is this something that can be done with the models, or is it complex to model it for the moment? At least
at the moment, a triple star evolution is a bit complex. I'm not so sure how to do this in MESA yet, but maybe we can make some assumptions and assume just start off with a wider system and take away angular momentum, because that's what a third star would end up doing, and try to see what that might do to these more massive contact binaries and how their period would end up changing in this case.
Okay, and then I have to, from an observational point of view, I have two extra questions here. One is, in the case of the mergers, you expect a not negligible percentage of massive binaries ending up as mergers. It's 20% more or less, no? So what are the observational evidences that you expect to have from the merger itself? So I mean, this is not an easy process, no? This has to be very energetic, this merging. So do you expect to see something that could be detectable in whatever wavelength, or maybe?
You mean an actual merging?
Yeah. So when
there's only been one merger, I think. Yes.
Yeah, when the merging is taking place, what you expect from the observation, or this is something difficult to detect due to the time scale in which this happens?
Well, in the case, I think so far we've only seen one merging event take place conclusively, and that is I think B1309 Scorpii, and there's a typical light curve that comes out of this that they have modeled. Oh, lights have gone off. Okay, sorry. But I'm not so sure whether it would be detectable directly. There will be signatures left behind, maybe afterwards, that we can try to figure out. For example, in the case of 87A, we had very clear abundance patterns, the enhancement of nitrogen to carbon ratio, and all of these things. So post-merger, we can definitely maybe pick these up with the elemental abundances, their position in the HR diagram relative to the other population. These are some tracers we could use. And of course, if the star is rapidly rotating, then it's also very likely it began with a it actually was born out of a merger itself.
And this is exactly my other question is, I know that you are, the modelers are working hard to try to find clues to see if the star is a merger or not. Have you found something that is can guide us, the observers, like if you see this or that, it's likely a merger, or still is there are so many parameters to take into account that it's not so obvious, or expect that?
It's actually, that's the work I'd like to start doing as soon as possible at the ISC if I get the job. So actually to find merger products in a population. And as far as I know, there's been no. So first, for that, you need a proper homogeneous grid of models that systematically obtain these post-merger stars, and then we can make synthetic populations and then compare them with the data. This work has not been done, and it will take some time, and hopefully it will be done.
Okay, that would be great. Thanks.
Yes.
Okay, thank you. Are there any questions? Any student? No? They're being shy. Okay. Then I guess we can thank the speaker again. Thanks for this very interesting talk.
Welcome. And apologies for all the interesting interruptions as well.
No, well, that's part of the